It's Vlad Constantinescu, and I'm a machine learning engineer with Getvisibility. Hope everybody's got the pizza and the drinks. You're going to need them. It's a really tough act to follow the previous one because it's got so much. It's so important to sort of disseminate this information, and it's true that we kind of live in a bubble. But on this one, we are going to go into the nitty-gritty details of some of the machine learning approaches that we use. I really want this to be an open conversation, so please go ahead and just ask anything. It doesn't really matter. We'll just take it at whatever the pace it needs to go. What I'm going to be talking about is learning useful representations of data. What's that, and how it works inside the ML community, and what kind of problems it addresses. And it's going to be a technical presentation, so I'm going to be referencing papers, and there's even going to be some math, but I'm going to try to sort of wipe away the math and always explain what's going on in the background. That's the intuition. So at Getvisibility, what we do is we're trying to figure out on people's corporate networks, we're trying to give them a sense of what's going on with their data, what kind of sensitive information they have that would make them liable, or what kind of private information, or what kind of information they have in general on their huge networks. And we're using machine learning essentially to understand what's going on in people's data repositories, and then of course report to them because we want them to understand. That's what we're all about. So the summary is we're going to talk about representations of data in general, and where do they what's the role they play and why are they important? Why do we need to learn them in the context of machine learning? And then we're going to go through a few autoencoder models and sort of the more developed stuff that that's hot right now in artificial intelligence. How many of you guys have heard of autoencoders? Okay. So we're going to go through those and sort of evaluate what their impact is and where they're going. So first of all, let's talk about data representations for a second. So this is the kind of the formal definition that you will gain, but essentially a representation of data comes with a data generating process. That's something that happens in real life. Well, you have, for instance, a set of images that have been captured by something, by some camera perhaps on somebody's car, or a bunch of files that you want to analyze. Those have been generated by something, by people. They've maybe written them, or something was going on in the natural world, and they can be formulated as a probability distribution in some huge dimensional space. And generally, we don't have access to this probability distribution. We don't know what the data generating process is. We just see a bunch of samples. So, for instance, we see a bunch of pictures coming in, and we want to know if there's cats in them. Or we see all kinds of waveforms going in, from analyzing people's EKGs to sound analysis and voice interpretation and so on. We can see word sequences if we're analyzing text, and all kinds of data. And all these are just samples of the underlying distribution of the data generating process that we're trying to make sense of and understand, because we're trying to do what's quote-unquote the artificial intelligence part. So we have this process in the background. It's a natural process. There's something very complicated happening, and what we see is a bunch of samples coming in. This is a classic data set that's used in machine learning. It's called MNIST. It's, the problem here is identifying what digit people have written on their labels. And it's about 70,000 of them written by different people, and machine learning has to go through them and say this is a 6, this is a 7, this is a 4. And MNIST was sort of a benchmark problem. Now we have more complicated problems because essentially MNIST was licked off, so it's kind of at the maximum probability, at the maximum accuracy where it needs to be. But it's sort of the template example of a complex probability distribution. Like all these images, they can be shaped up as a probability distribution, and there's another mathematical formalism for linking them to their labels, which are the actual annotations. So now we go into more detail. We're going to talk a little bit about entropy. So Entropy is essentially a state of disorder, is a measure of disorder. When you when you hear about entropy, this is uncertainty should be the main handle that should sort of pop out. Entropy of a distribution is its degree of disorder. It's the uncertainty in predicting outcomes, and it's large when the distribution is really uncertain. So, for instance, if it were that I really don't know what's in this class, the entropy of the distribution of what's in it is large, and it goes to 0 if you're fairly certain what the outcome is going to be. So it's always like a positive number, and it's the basis for defining in a certain sense what a representation of data is. A representation of data is something that takes the original data, let's say the NIST images, and it builds a scheme of encoding it in such a way that the conditional entropy goes to 0 and that the entropy of the representation is non-zero, essentially. Because we're interested in holding something called, maximizing something called mutual information between the underlying distribution and the posterior distribution, or our latent labeling. So examples of representations in everyday life, you know how you have your phone book and there's a number that you can number it from 1 to 120 contacts in your phone book? The ID of a contact in the phone book is an example of a representation. It's not necessarily very informative because you can't necessarily reconstruct the contact from an ID, but it is a representation. You can just look at certain aspects of something and call that a representation if all you need to know is about a car is its color, and that's a representation of the car. You simply don't need to know the rest. So it's a very loose understanding of the data generating processes and of the distributions around us. This is an example. So we have NIST over here. Each one of them is a independent sampling of the NIST problem. We don't know the underlying process, and what we're trying to do is find a way to take every one of these pictures, potentially with their labels, to some number or some vector in some latent space. That's the representation. And we want the conditional entropy to be small, to go to 0. So that means the uncertainty when we have a digit, where it goes has to be small. If I give you a digit, it has to go to one place, and that's it. And we want the entropy of the representation to be larger than 0. So we don't really want, for any given digit, everything to go to a single point in my latent space, because that wouldn't really carry information about the distribution I'm trying to represent. So generally, by the way, I think I should kind of slow down. I'm not sure if anybody has any questions at any time, please go ahead. We are interested in a specific kind of representation which is invertible. So when you take an object, a sample of data that you see, and you bring it into your latent representation, you also want to bring it back to manufacture. So for instance, create digits, build maybe a generative system of the data that you've seen and reproduce it. And this is the stuff that sort of comes down to building an encoder function and a decoder function. Encoder is generally the system that takes you from the original distribution to the representation, and the decoder is usually what you would use to go back to the original distribution to build maybe a generative system. So this is how it looks usually. This is what we do in learning representations. We get a bunch of samples, we take them to the latent space, and we're trying to build a system which takes them as faithfully and accurately to something that we understand and we can work with, from something which is really complex, which is the samples that we have in the data generating distribution. So this is the trickier part, is why do we need to learn representation? Why can't we just do deep learning and AI and it will work? I mean, why is this even important, this stuff? Well, first of all, there are some problems that people started to notice with AI, and one of them is the black box problem. So, it's been mentioned previously. These AI systems, they're seeing a lot of data, and essentially they're training their parameters, finely tuning on the training set, and you don't really know what those numbers mean, right? So it'd be really cool if you could slice them up in certain ways and understand what they have inside, and maybe even check that, and so on. But the underlying problem is a little bit more sophisticated, and it comes down to something called Kolmogorov complexity. So is this how? complexity is usually something vague in the dictionary, but this thing is really a very solid formalism for understanding complexity. And the way you can think about it is that is the minimal program that would generate the object. So the complexity of, let's say, this glass of water is the size of the smallest program that can describe it, essentially, on some Turing machine, all right? Now, the computer, or by presentation perhaps, it's a little bit more complex. You need a larger program to generate it, or to describe it, than maybe something like this. So we can talk about the complexity of objects, we can talk about the complexity. Complexity was originally defined by Kolmogorov on binary strings and numbers, but we can talk about the complexity of all kinds of things, including probability distributions. And since we're working with probability distributions, we're trying to solve inference problems, we're interested in the complexity of probability distributions. So, okay, we've learned how to detect cats in people's videos on YouTube, but how complex is that task? How many degrees of freedom do I need to have in that system for it to work, minimally? How large is the program that somebody would have to sit down and write to make that work, right? It's pretty large. That's why we use machine learning, because we're trying to approach problems which are really too difficult for people to sit down. It would take them too long. You have to sort of teach the system from examples. So complexity is the program, the length of the program that you would need to write to obtain your object. It's measured in bits, right? Because it's the length of a program. Essentially, it's the length of a Turing machine, if you want the more general definition. And you can also define a conditional complexity of something. So what if I had some sort of a library that would describe some of the objects? Potentially, then the program would be shorter, right? We use that all the time. We do that all the time, especially in software engineering. You write something, you call on to all kinds of libraries that make your code a lot easier to read, shorter and more compact, because then you would have, otherwise you have to write everything in assembly and it would be huge, right? So the problem here is there is a way to lower the complexity of a problem by conditioning it on a different problem. That's what I want to point out. So a few examples. This is essentially a simple object. It's a distribution, it's a normal distribution. You can write it in a few lines of code. Now, complexity is not something that you can really measure, because you can only measure it up to a constant. It's not measurable by definition, and there's been a lot of work on this. But you can sort of size it up depending on the machine you're looking at. You can definitely look at it as the size of the program, or maybe even the size of the compressed text. This is a simple object because you can pretty much write a simple program in Python which would more or less generate it. Python, of course, has a lot of complexity behind it, but in this case, it would sort of make sense to do it like this. So some other objects look complex, but they're really not. This is a Julia set. It's a fractal. It's just an interesting picture. You know, I could give another example of complex object. So the Julia set itself has infinite complexity because it's an infinite iteration of a rule. So it goes infinitely deep, and you wouldn't be able to write a finite program to generate the entire Julia set to sort of pinpoint for every point how fast it iterates. But for some representation of it, so if you just iterate for a small number of times, or you just look at a picture of it, or something like that, the complexity is small because we know how the Julia set is generated. It's just a few mathematical rules that we apply iteratively. So the smallest program that we can write to generate this picture is pretty small compared to how awful the picture looks, right? And this is an example of an object that may be simpler than it looks like. And the rabbit hole goes really deep on this one because, for instance, you notice that it's self-similar. It's a trait of fractals, right? So if you can analyze it in a way where you look at each one of these pieces separately and then integrate the information from the smaller pieces and the larger pieces, it kind of makes sense to look at it that way. That is an example of a rather simple object that doesn't necessarily pass the test in complexity. Another observation on complexity is that you can transform problems. You can transform things. You can reduce their apparent complexity by leveraging this conditional complexity thing. So essentially, let's say we're looking at faces. It's not a typical data set in the machine learning community. And we are trying to identify maybe if somebody is blinking, there was a previous example with identifying somebody's posture, see if they're tired or something like that. It is a lot easier to break down the face, and this is what's actually going on in many of the machine learning approaches to understand faces. It's a lot easier to break it down in basic elements and then integrate those into more complicated elements with conditional complexity over here, and then so on until you integrate to the face level and come up with apparently less complexity than if you were to analyze the face as a whole. All of a sudden, just look at the picture and so on. And the final idea is that noise is complicated. So noise is complicated because if you have a sample of noise, then essentially you can't find a way to write, you can't really write a program that will describe the sample of noise in fewer lines of code than simply memorizing it. It has maximal complexity. You just have to memorize it and that's it. Of course, you can generate a different sample of noise, but for this particular one, there is no rule behind it. There's just no way of making any sense of it. And we're surrounded by this kind of noise. Virtually any kind of statistical inference problem has some part that you can learn, and you can draw inference and extract rules from, and maybe build a representation, and some part that you can't. It's just noise. It's just data, irreducible noise, and it's going to be there forever. So we come down to the actual reason why we're trying to learn representations. We're trying to learn representations of data because we're hoping to reduce the complexity of the inference problems that we're trying to solve later on. And think about it as we're trying to find a way to write libraries for software that we're going to use later. Because with a good representation, it's actually easier to solve a problem than without the representation. The inference system that you would deploy to solve that problem based on the representation is simpler. It has lower complexity. You have fewer degrees of freedom you have to play with. And there's this thing that simpler solutions, Occam's razor, William of Ockham, simple solutions generalize better in general. You're trying to find a simple way to fit the observations, the evidence that you see, rather than a complicated one. And this goes back to a lot of research in algorithmic information theory, Solomonov induction, universal prior, and so on. This is a representation that can be used to solve NIST. It's a two-dimensional representation. So imagine this is a plane, and at every point in the plane, evenly spaced, I sample what's the most probable thing that would match at that point in the plane. And you can see that these guys look like digits, right? And I can use a simple linear estimator to solve this to about 98% with this, because if you look closely, you'll see that the shapes are of a different digit in different directions. So over here we have the 7s, over here we kind of have the 1s and the 0s and the 8s and the 3s and the 2s and the 6s and whatever. So this is an example of if you have this thing and you just match it to the NIST digits and then you build a very simple estimator on top of it, you can solve it to a greater extent than you would just be able to with the estimator. NIST is usually solvable to about 92% accuracy with linear estimators, and the state of the art is 99.8, I think. That's about it. There's not much more you can do except for that. So one of the things that we keep hearing about deep learning and artificial intelligence in general is that it needs a lot of data. It's a lot of examples. And these are sort of examples of deep learning systems that are in the state of the art that have been published a lot. They're winning images competitions and so on. And these are the data sets that they've been trained on. They've been trained on huge data sets, 1.2 million images with categories, videos, 6 million sentence pairs, the GLOVE 6B corpus, which is a word-to-vec corpus, 6 billion words. You need a lot of data to train a neural network because it has so many degrees of freedom that in order to adjust each one of them to just the right value to explain what you see, you need to see a lot of stuff, right? So the challenge here is if we can build a pre-trained representation that is salient, that exposes the right features for us to solve our problem, then we would essentially need far fewer examples for the main inference problem that we're trying to use. And this is, apart from, problems with bias and so on, And apart from the potential problems with deploying these large systems, let's say if we want to do driving cars, autonomous cars, and they'll maybe crash, and all kinds of issues that can appear if we integrate robots too closely in our day-to-day life. One of the problems we have right now is that deep learning needs a lot of data. So if you try to start a company in deep learning, you'll find out soon that you hire the machine learning engineer and they tell you, give me more data. Because I've trained the system, and the system is maybe overfitting, and I just need more examples. What do? You get more data. But it's expensive, because generally you try to get labeled examples of the problem you're trying to solve, and they may be difficult to, or even impossible, for instance, if you're trying to get access to patient records to solve healthcare problems. So the idea would be to use unsupervised learning, so just understanding the distributions, to draw the relevant factors out of them, come up with ways to make them salient, so important for the problems that you're trying to solve, in order to reduce the complexity in a Kolmogorov sense of the system that's trying to solve the problems, and therefore reduce the cost of your data. This is the big deal. This is why it is important that we have a way of understanding how to learn representations of the day-to-day world. So there was a lot of hype in the deep learning community at some point about unsupervised pre-training. This is not quite it. That was a technique of sort of getting into a region of the model parameter space where you would get better results. This, over here, we're talking about effectively slicing models into intermediary representations and then diminishing the amount of supervised labeled information that we use, because unsupervised information is a lot cheaper. So for instance, if you're trying to teach a system how to, let's come up with a deep learning example, something that people do. You're trying to see, let's do the cat videos thing. So you're trying to see, this is what Google started with. So you're trying to see for every video if it's about a cat, if there's a cat in them. And they had this huge corpus of YouTube videos that they would have all kinds of stuff in them. And at some point, they would have a classifier, and they would go through these massive convolutional neural networks, and the classifier would say, I've spotted a cat, or not. And of course now, if you're just looking at videos of cats, those are not necessarily expensive. You can gather a huge corpus of them and just train them, and you get 99% accuracy. Everybody's happy, machine learning engineers back there, that's it. But it may be that you can't. So the idea is to learn a representation of the videos. So to get the videos through an unsupervised learning system, and not necessarily videos with cats. You can just grab all the videos on YouTube and train some kind of system which reduces them to a smaller dimensionality, eats up a lot of the complexity of the underlying distribution, and then build a simpler system which essentially needs fewer examples to solve your problem. So my question is, does this make sense so far? What we're trying, it's essentially about cracking the black box and reducing the cost of making AI really smart. That's what we're trying to do. So one initial way of doing this is, okay, we have all these words, we have unsupervised learning and data representations, but how exactly do we do it, right? What are the approaches that we use generally to do this, to achieve these objectives of maybe gaining a better understanding of the data before somebody has to label it, and we have to go through that expensive process of curating it and creating corpora and so on. And the original, the formal way of looking at this is something called maximum likelihood estimation. So this is a method that was invented by the mathematician Ronald Fisher at the turn of the 20th century. It's essentially a way of adjusting the parameters of your massive neural network with many, many weights in such a way that it solves your problem and not a different problem, right? The reason we use maximum likelihood estimation is because other statistical inference approaches are really impractical for the kind of problems that we're trying to solve. So this is sort of a cheap way to do it, essentially. We're trying to get out of using full Bayesian inference, learning the entire distribution. We're just trying to tune the weights of a massive neural network in such a way that it looks like it's solving the problem. And essentially, this is the reason why it's not necessarily obvious what the network does, because those links just get tuned in a very specific way. It's also the reason why it's very easy to fool the network, especially if it's overfit, by giving it a sample that makes it misbehave. Which is why we really shouldn't trust these systems too much unless we really understand what's going on inside them by learning representations. So the autoencoder is essentially two neural networks. That's all it is. It is one neural network that takes in the picture and creates a vector in the Latin representation, and another one which essentially takes the Latin representation and brings back a picture. And the way we train them is we get a few examples of our original representation. So these are NIST digits, but it could be as well videos of cats or pictures of people with their eyes closed or eyes open if we're trying to look at whether they're sleeping on a wheel or something. And we get them independently, so we're interested in independent occurrences of the same phenomenon because we're trying to understand the probability distribution behind it, the law that is generating that phenomenon. We pass them through the encoder, which has not been trained. It's a parametric system, but we just randomly assign the values in there. And we obtain for each one of these independent samples a representation in the Latin space. And then we bring back the representation from the Latin space, and we obtain a bunch of pictures. Because we've assigned the parameters randomly, what happens is those pictures are going to be completely corrupted. They won't make any sense compared to the original object that we've put into the autoencoder. But what we do is we take the gradient of our loss, which is something we do often in deep learning. So we have a loss function that's set up as a maximum likelihood estimation objective. We just do some tricky math to basically understand how do we change the parameters of this system so that the reply that we got from it is closer to the truth. So we adjust this massive neural network in a very precise way, well, not really precise because it's a stochastic process, that would make it behave better based on what's seen in the Latin space. And then, and then we take the other one and we do the same thing. So once we have the Latin representation, we take its gradient and we try to adjust this guy to get the Latin representation closer to where it should be, so that this guy reconstructs the original image in a better way, with more fidelity. The net result of this process is that if we take any image from this thing or any object that we're trying to learn a representation for, and we train this thing for a number of iterations depending on the complexity of the problem. It can be something that works on your laptop in 10 minutes, or it can be something that works on a huge data center in weeks and weeks of training. What's going to happen at some point, because the maximum likelihood estimator is convergent usually, what's going to happen is that if you take this, it goes into a specific point in the Latin space, and then it comes back as a picture that's very close to the original. So both the encoder and the decoder are doing the job, and this is an actual representation of the distribution that I have originally. The problem is that this kind of distribution is not really salient. So the autoencoder is just a pair of neural networks which have learned how to take an original object, an image, or something like that, and into a posterior space and posterior representation, and bring them back as another image. But it doesn't necessarily learn something that helps me solve subsequent problems, because these are just numbers. It's just learning to take an image into a vector and then bring it back as an image as close to the original one as possible. There's no guarantee that I will actually be able to use that in any meaningful way. So people started thinking about, what do we do? How should we learn these representations with the autoencoder, which is a very flexible concept, in such a way that the features that I obtain here, this stuff, is going to make it easier for me to solve subsequent problems. And this is where most of the state of the art is right now. What do we do? There are a bunch of approaches to it. In the early 2010s, they started adjusting the posterior representation. We're trying to maybe make a sparse representation of the data. Maybe we're trying to contract there's something called the manifold hypothesis. Are you guys familiar with that? So there's this idea that all this information that we have floating around us in the everyday world is actually really simple, and it compresses into a low-dimensional manifold. So if you take a picture is like what? 1,000 pixels by 700 pixels. That's a few million pixels. That's the 7 megapixels on your camera. It's got 7 million dimensions because each pixel you can assign a color to independently, right? But the actual information in the picture, let's say you're trying to pick out faces or something like that. There aren't that many faces, right? The actual information is on a manifold that's maybe 20 dimensions or something, or even less, right? That's a lot of room. So the idea is that your original image, you put it through a representation that sort of compresses it into something simpler. And that's why we're trying to do all this. Another problem with the basic autoencoder that people encountered while trying to train them was that it's not really useful because, in the sense that it's not really a generative system. So we can't really pick a point in my latent representation and manufacture an image in my original distribution. Because I don't know what the latent representation looks like. It's just something that the autoencoder has learned. I don't really know what the probability distribution for that is. And there's some really nice papers on this called stochastic gradient variational base. This stuff is basically this. The variational autoencoder, which is one way of making sure that if I have some evidence, which is I have some samples from a probability distribution that I'm trying to learn, and I'm trying to put them in a latent space, then I'm going to know what this space looks like. So it's a little bit more complicated. What we do is we sample from the distribution, from the original distribution of evidence, and instead of predicting the latent space directly, we predict the parameters of another distribution, and then we use those to sample again. This essentially constricts the information at this area because we are adding noise. It's a somewhat similar concept is used in denoising autoencoders, but these are corrupted at the entrance, so this is a far more efficient way to reduce the amount of information that comes in from the distribution of origin. So we get like a region of confidence, a distribution in the latent space, which we use to sample back and obtain a sample. So it's an autoencoder, but which is constructed in a certain way that when I adjust the weights here and then here, when I do simple stochastic gradient descent, what happens is that not only the samples that I get through the latent representations and back have high fidelity, so they're accurate reconstructions of what I had originally, but at the same time, I know how this guy looks. So it looks maybe like a multivariate Gaussian. I can take a point out of it and I will obtain an image. That's the classical example. So it's interesting because this can be used to generate things. So you train it on faces, and it can be used to generate artificial faces. So that's what we're trying to do here, right? Reconstruct originally we're doing reconstruction, but what we can do is throw the first part away and just generate by picking up a random sample from this guy. So we're only interested in the decoder. So as an example, these are artificial faces generated by a variational autoencoder. These people don't exist. This is a system that has been looking at faces for a long time. It has been understanding what is a face and what is not a face, and then it's been asked by randomly sampling from its posterior distribution to generate the face. And this is what it looks like. As you'll notice, these faces are somewhat symmetrical and therefore attractive because the autoencoder is trying to contract the amount of information it gets from the input distribution as much as possible, and you need a lot less information if you have a symmetric face. So most of this stuff, and also there's a lot of paperwork on why they're blurry. That's really interesting right now. So the latest, hottest thing in learning representation right now is something called contrastive learning. It originally started as the idea that you can't really learn an autoencoder of words because there's too many of them. So if we were to try to pick up words and then pick up a word, encode it into some meaningful representation, and then turn it back, each one of us uses what, 2,000 at minimum, if you're barely starting to learn a foreign language, you have to use at least a couple of thousand words, right, to just get by on the street. But usually we use more, 20,000, 300,000, maybe if you're trying to parse a really technical corpus, right? So there was this idea that instead of learning the complete autoencoder, maybe what we do is we train something, where a system which simply discriminates between an accurate sample from my data generating distribution and random noise I'm just constructing. So this was the principle behind noise contrastive estimation. It was introduced by guys in Finland, by the way. So Helsinki has, because it's been mentioned before, Helsinki has really interesting contributions in the independent component analysis, and this thing was introduced by them. And it was originally used for, and it's used mainly for natural language processing because of something called data sparsity. So in natural language, the sequences of words that make up something that we use in speech are few. We don't really pack that much information in everyday speech, right? So if I were to create a random sequence of words, cucumber, computer, glass of water, that's not necessarily something somebody would say, right? Random sequences of words are very likely to be mumbo jumbo. So you can easily generate them and maybe use that to train a system which would discriminate between random sequences of words and actual sequences of words. And you don't really need the full autoencoder for that. So the way it works, this is not the way it works. So the actual implementation of this is usually in something called the Skipgram model. So what we're trying to do is predict if a combination of words is valid or not. Over here, we're using a simple prediction with NIST because this is the basic process, and then it's been developed a lot into the natural language processing systems that maybe we use in our phones. So we have a distribution. We have the real samples that are coming from a distribution, and we're trying to put them through the encoder, which is an embedding into the latent space. And we're also training a discriminator. This is a neural network which says, okay, you've put the sample here. Is this coming from the original distribution or is this noise? Just random noise. Although in negative sample or in some of the implementations, the noise is carefully created such that it's very close to the original distribution, right? So what we do is we sample a bunch of images, of word combinations. We sample them from the real distribution. We look at maybe Wikipedia and what people write, and we sample them from a noise distribution. And we mix them up, the noisy samples with the real samples. And we're trying to push them forward into our latent space and then through the discriminator. And here a system predicts if parts of the sample are fake or are they real. That's the way it works. And it adjusts itself based on the prediction, and it also passes back the gradients into the system that builds the representation. So what happens is we kind of obtain a representation of our original distribution just by this guy doing that job, which has nothing to do with what we wanted to do originally, essentially. The problem with this is that this guy quickly learns how to discriminate between a real sample and a fake sample. It's generally difficult to craft noise that would fool this guy. It's only easy for certain specific problems, especially in the field of natural language processing. But if you try to apply noise contrastive estimation or negative sampling to pictures, it won't really work because it finds simple stuff like, this is not a digit because the hue the density is not really right. So it learns something completely simple, and there's no guarantee that the representation we've learned is okay. So people started thinking, how do we generate noise which is closer and closer to the original distribution, right? We want to generate noise which is really difficult to tell from the original distribution. We want this noise to be corrupted, examples of this guy, such that this guy has a tough job to do. So this is adversarial modeling. With the basic model is generative adversarial network, which is the state of the art today. It's being used to, essentially it's noise contrastive estimation turned upside down. What we're doing is we're drawing random samples from our latent space, and we're generating them. These are our noisy samples, and then we're drawing real samples from our training set and putting them through the discriminator. And this process is just the same process that we had in noise contrastive estimation. It's just that we've moved this guy from here to here. And we pass the gradients of the estimation problem down into the generator. We want the generator every time to get better and better at approximating the real distribution. So this game gets tougher and tougher for both players. It gets tougher for this guy because he has to get closer and closer to the real samples. And it gets tougher for this guy because he has samples that are more and more difficult to separate between the real samples. So the net effect of this training procedure, which astonishingly works, that was a major contribution of the paper, was that this guy gets better at discriminating samples between noise and real samples, and this guy gets better at generating realistic samples. And this is what we're interested in. We're interested in this representation, which is going into our real system. So this is the net result of the process, and this is another collection of faces. It's organized on 5 columns. To the left, you have real faces, and to the right, you have a manufactured face that is closest to the real face on the left. As you can see, these is the celeb faces data set. These are all celebrities. So these are the real celebrities, and this is what the generative adversarial network has learned to approximate closer to the real celebrity. Some of these look good, some of these don't. Nobody's perfect. Like, look at this one. That's my favorite. There are still issues with the generative systems. It's a field of intense research, but they're getting better. I mean, this is how you manufacture data. You show an artificial intelligence system pictures of chairs, it manufactures pictures of chairs for you. This is how artificial intelligence systems create art. You just show them so many paintings, at some point they're going to learn what a painting is, and they're going to manufacture paintings for you, which are different than the ones you've shown it. Music, there are startups trying to create music, and it's going to sound really good. So right now we are at the beginning. We don't have that many parameters, but they're getting better and better. And this is one of the ways they're doing it. So at this point, I'm just going to open the floor for Q&A. And I just want to end up closing that it's a really exciting field to be in, and it's got a lot of potential, and it's really important that we try to sort of uncover as much of the details behind the scenes, and we try to expose what we're actually doing, because essentially in the background it's just a bunch of math, and that's all we're doing, and we're trying to make it closer and closer to reality every day. So if there are any questions regarding any of the models, sure, please go ahead.
I wanted to ask about the MN IST dataset.
Yes.
So I tried myself just for fun, just to show to the family. I used one of the new trained neural networks that are giving around 99% accuracy.
Yes.
I tried to build a canvas with JavaScript, simple JavaScript, so for family business. So if you draw the, it was done with the fast. If you draw the number, then it will show you the guess.
Yes.
But I must say that the accuracy wasn't anywhere around 90%. I would say with some numbers it was like 5%. So, like especially with the one, if there's only a certain way that the neural network can accept one, no. So I'm asking, what is actually that neural network, neural learning down there? Because it's definitely not learning recognizing digits, even if it says digit recognition. But the neural network wasn't, it was giving 99% accuracy, but it wasn't recognizing digits.
So the question is specifically about NIST. NIST is a standard, it's a very good question. It's a standard data set. It has 60,000 digits for training purposes, and it has 10,000 digits on which they're different, or they're written by different people perhaps, on which you validate. So you train on 60,000 digits, you see the picture and you have to say if it's a 6 or a 5 or whatever, and you have another portion of the NIST which was written by different people on which you validate. And then this information was curated, the digits were aligned, were put in the middle of everything, and a lot of irregularity was removed because they wanted to keep the amount of examples close to a minimum. And we get back to complexity. There's a paper from Uber where they try to evaluate the complexity of the NIST problem by sort of training the neural network in a special way. And they're trying to figure out how many degrees of freedom, how many parameters do you actually need to learn NIST? To learn NIST means just solving the problem on their test set, right? So getting to that 98% accuracy. And it turns out that you don't need that many. With a convolutional neural network, you need like 200 degrees of freedom, and with feed-forward, you need like 700. So the NIST problem itself is not that complicated. As it stands, the network doesn't know what a digit is. It just learns correlations between different pixels in the image and how they lead to inference about what a digit is. But it just learns that, so it learns a small complexity problem. And if you go away from the problem in any meaningful way, like you write your 1 in a corner, that's never seen that. It doesn't know what a digit is. It just learns certain statistical correlations on the data set that's been trained on, and that is not necessarily such a complex problem. It collapses with 200 degrees of freedom for a convolutional network. Those statistical correlations get embedded into the system, and it gets very good at solving the NIST problem. The phenomenon you're describing is called overfit, essentially. So in the general case, not for the NIST problem, the system that has tweaked those roughly 200, in reality there are many more in the conventional neural networks, but once the system has figured out a way to tweak the parameters to solve it on the test set, essentially there's no guarantee that if you show it something outside of the test set, it's going to behave in the same way. And the question is really good because it goes into what are these things learning, right? Everybody's asking that, why are they such a black box? And the answer would be, well, we kind of need to create intermediate, the data around us is so complex, so when somebody writes down a number, they have like years of school experience, and they have all these little systems that are working to create, the data generating process is really more complicated than the 60,000 examples that the neural network sees, and the 10,000 examples that it trained on may lead on to. So that's why you kind of need to learn about the world in a more progressive way by sort of incrementally learning these representations and then solving the problem. But that's neither here nor there because NIST is more of a benchmark. It's not really designed to be a problem that would get you a good trackpad software. It's the kind of problem that you throw at an ML engineer when you want something really, you just want to see how a model works and you want some preliminary information because you can download it in 3 lines of code and see how everything works. So in summary, the main reason it doesn't work is because NIST has been curated to show the digits in a certain way, and maybe you've drawn it a little bit differently than the way it's been working. The long answer is that it's at the same time an overfit case and maybe a very simple problem that has nothing to do with actually writing digits, which is perhaps a much more complicated process. Okay, so that's it from my side. Thank you guys for listening. I hope we get at least the idea is that essentially if we learn representations, we are going to be able to reduce the cost of training these systems, because at some point it's really problematic. And this would mean that you will see many more AI startups having interesting ideas because they get a lower barrier of entry to the market, and everybody gets to like train their network and have their idea implemented with less cost. That is the basic idea behind learning representations. Thank you very much for listening, and